Welcome everyone to the OpenACC course. Thanks again for joining us today and keeping up with the course material as well. We hope that you're enjoying the course and find it useful for the projects you're working on right now or plan to start on. My name is Julia Levidas. I'm a product manager at NVIDIA Tesla Group and will be helping with the class. So just a reminder that all class recordings will be posted on the course page by the end of the week. We also have posted all the recordings from the previous 2 lectures, so please go to the course page to review the recordings from the previous lectures. Their link has been posted to the Q&A pod, so please refer to that link to download all the recordings. Also, there have been a lot of questions regarding the certification. So this certification, for those who attended the live sessions, will start tomorrow, November 10th. The certification is a set of questions that will cover basics of OpenACC, as well as some results from your home assignments referring to the quick labs. Again, so the certification will be available to those who attended live lectures, and we will open certification tomorrow, November 10th. So by tomorrow, those who attended the lectures will receive the link to complete the certification. We will be also giving you certificates once you completed the certification. This certificate will arrive to you by email as a PDF file. And going back to the lecture today, so all the lines right now are muted, so please submit your questions through a Q&A pod on the right-hand side toward the bottom of the screen. We're appreciated if you post all the questions to all panelists, so it will be easier for us to go through the questions, as well as please do not use the chat window unless you have something urgent, like some question with audio or video. Otherwise, it's really hard for us to monitor multiple pods. So I appreciate if you use just Q&A. So today we have 3 instructors. So I have high confidence that we'll be able to cover all the questions you have. Matt Colgrove and Rob Cravella will be in the background answering your questions for the Q&A. Both of them have been instructors for this course before, and they also gave this course to other students. So they're very experienced and knowledgeable trainers. So I believe you will like it to have 3 of them today, for sure. So Matt is a developer technology engineer in PGI, working on compilers and tools with focus on customer support and OpenACC training. Bob is a solution architect at NVIDIA, and one of his responsibilities is to give trainings, including OpenACC. So Jeff is our main instructor today. He is a software engineer at NVIDIA's Developer Technology Group, where he works on porting and optimizing HPC applications. He is closely involved with the development of both OpenACC and OpenMP specifications. So I believe we're done with all the logistics and ready to start.
Hi, everybody. My name is Jeff Larkin, as Julia just introduced. Welcome to this course. This is the 3rd week of the course. If you've missed any weeks, all of the videos are available online, and the link will come up here in just a moment, but it's the same website where you signed up. Just a reminder, if you're either just joining the course or just need a refresher here, the objective of this course is we want to enable you to accelerate your applications, the things that you care about most, using OpenACC. We presented this to you in a 3-week course. The first week we focused on parts 1 and 2 of our 3-step process, analyzing and parallelizing your code with OpenACC, and we talked about some profiling tools and how to add OpenACC to a simple application. Last week we talked about some optimizations. Particularly, we talked about optimizing your data movement if you have a GPU with physically distinct memory from the CPU, and also some loop transformations that you can do to better optimize your code. This week we've titled Advanced OpenACC, but it's really just a mixture of topics, some of them advanced, some of them not, that just don't fit neatly into those other 2 weeks. Things we think are important enough that you need to see as a part of this course, but just didn't fit with those weeks. And so this week is the Advanced OpenACC. And today's objectives, first, we want to make sure that you, I want to present to you some common refactoring techniques that I've come across in porting OpenACC applications. Several of these I had intended to present last week, but just due to time didn't get around to, so I've put them into this week. I also want to present to you the OpenACC routine directive. It's an important directive when porting many applications that enables you to use OpenACC throughout your entire application, and we'll discuss that in just a few slides. And then we're going to spend the bulk of the presentation talking about programming with asynchronous style, so that you can send work off to, say, a GPU and continue to work on the CPU to either send more work or perhaps to even work on across multiple GPUs. And then we're going to use a technique called pipelining to do that. And lastly, I want to talk a little bit about OpenACC interoperability. So, demonstrate that when you choose to start porting an application with OpenACC, it's not a choice of OpenACC or other technologies, but OpenACC works well with accelerated libraries and with CUDA as well. So, getting started, some additional optimizations. And again, some of these, if you download the slides from last week, these slides were actually in there, just we didn't get a chance to go over them. And the first technique that I want to talk about is the collapse clause. Now, we talked about the idea of clauses last week with the data clauses. A clause is something you add to the end of your directive to give some additional information. So in the form of data clauses, the additional information was how to manage your data, the size of your array, or how to move the data. In this case, this is a clause that you add to the loop directive that gives the compiler more information about your loops and transformations that it can make on the loop. Specifically, if you look at a collapse clause, it's intended to be applied to a tightly nested group of loops. And what I mean by tightly nested, if you can picture on the, or look here on the left, you can see we have a for loop, and immediately within that for loop is another for loop. And it's common in scientific applications to have many of these all together. And what makes them tightly nested is there's no code that exists between them. It's just loop followed by loop followed by loop. The collapse directive takes some number of loops, so you pass in a parameter n, and that number of tightly nested loops, the compiler is instructed to fold them into one loop. So if you see here on the left box, we have 2 loops, and I've said collapse 2, and the compiler is going to transform that for me into a single loop that covers the entire iteration space. And so I, as a programmer, could do this transformation myself, but it's a little bit tedious because I would have to make sure that I get all of the indices correct within my various data structures in order to get this right. Here I've instructed the compiler to do this for me. And of course, the more loops in a loop nest, if I have 3, 4, 5, I've seen as high as 7, 8, or 9 loop nests deep before, it becomes more difficult and more error prone. So having the compiler do this for you is really valuable. And as a matter of fact, I would actually say that behind the data directives, behind the data clauses, the collapse clause is the most important clause I've encountered in OpenACC. So why is that? Why is it useful to take multiple loops and to collapse them together into one? Well, we talked a little bit last week, actually quite a bit, about OpenACC's levels of parallelism. And we talked about on the outermost level of parallelism is gangs. And gangs, if you're a CUDA programmer, equates to thread blocks. These are independent chunks of threads that operate on independent data. And so as part of running on a GPU, GPUs like to have lots and lots of thread blocks, so they like to have lots and lots of gangs. And so if you have a loop nest and your outer loop doesn't have very many iterations, then you're not going to produce very many gangs. So if you can imagine, if I have so maybe I can collapse 2 of them together, and I can have 100 loop iterations that I can break up into gangs. And if I collapse all 3 of them together, I'd have 1,000. And so that gives a lot more work to spread across the GPU. And by spreading this independent work, it allows the GPU to kind of load balance and keep itself busy. So collapsing outer loops to generate more gangs is a really good trick to optimizing the code. Collapse also works well if you have short inner loops. And so we talked about the tighter end of the parallelism within OpenACC, which is vector parallelism. And with a vector parallelism, you have some number of data elements, and all of them are being operated on at the same time using the same instruction. So on a CPU, you would have the SIMD, single instruction, multiple data instructions that operate, take in, say, 4 floats and perform a multiply across all 4 of those floats. On a GPU, we have this notion that we discussed last week of warps, which are 32 threads that are working, and each thread is executing the exact same instruction at the same time, but doing it on different data. So this is the vector style of tight grain parallelism. Well, if you have very short loops on the inside of your loop nest, well, sometimes there's not enough work to really vectorize. One of the codes I'm fairly familiar with, which is a climate code, has very short inner loops during part of its calculation, where the innermost loops are 4 by 4. Well, vectorizing across 4 elements is going to be really inefficient on a GPU because we expect vector lengths of at least 32. If I collapse the 2 of them together, I can get up to at least 16. And actually, if I go one level up their call stack, I can actually expand that even more. So it's also useful if you have very short loops on the inside of your calculation to collapse them together to get a longer vector length. But really the ideal situation is if you happen to have just a very deep nest of loops and can collapse them fully. So on the example up top here, there are 2 loops and I can fully collapse them together by using collapse 2. But no matter how many loops, maybe you have 5 deep or 7 deep, if you can collapse them all together, that just gives the compiler complete freedom of how to parallelize your code, and that's a really good situation. Particularly on GPUs, having as much parallelism as you can is always going to result in better performance. So collapsing your loops is probably, again, behind optimizing your data movement, collapsing your loops is probably the most important optimization, the most important loop transformation that you can do. Now, there's one downside to collapsing, and that is on particular algorithms that can exploit locality in your data. And what I mean by that is if I'm operating on one element, then I'm very likely to operate on elements nearby. So in this case, I'm talking about spatial locality. So this array element, by accessing this array element, I'm very likely to access ones around it. Think of, if you're familiar with stencil operations, it's a common sort of situation where I would calculate myself by looking at my neighbors. Well, in the cases and algorithms that have this sort of spatial data locality, collapsing them, like I've shown here, you lose all of that. Unless your locality happens to be in one dimension, I lose the second or third or however many dimensions of my data locality. So in those sorts of algorithms, collapsing is probably not your best bet. But OpenACC has another directive that works well in those situations, and that is the tile clause. So where the collapse clause would have taken this I and j loop I'm showing here and flattened them out to one long loop, the tile clause instead tells the compiler to transform it into smaller blocks. And so you can see on the left, if I have this 8 by 8 matrix I'm operating on, so here I would have 8 rows on the I loop and 8 columns in the j loop, I'm informing the compiler, tile that for me into 4 by 4 chunks. And so you can see here a green chunk, a light blue chunk, a dark blue chunk, and a red chunk. And within those chunks, this particular code here, which is solving the Laplace heat equation, will be able to exploit the spatial data locality within each of these blocks. So reuse the data within this green block as much as possible. So for these types of operations where you have a high amount of spatial data locality, then the tile clause is also a pretty good optimization here. In terms of the performance you can gain with the tile clause, I've seen fairly modest gains of maybe 10 to 15%, and with the collapse clause, depending on the code, I've actually seen much greater performance enhancements by adding collapse, again, to exploit more parallelism, to take parallelism from more of your loops. Okay, so that's two important optimization clauses you can use in OpenACC, and those are very simple to apply. Just add this additional clause to your OpenACC directive, and the compiler does the transformations for you. Not all optimizations can be done by the compiler, though. A particular optimization I come across a lot is optimizing your data access patterns so that you're always accessing your data in a stride 1 manner. What I mean by stride 1 is if I'm accessing element 0, my next loop iteration should access element 1, and my next iteration 2, and so on. So we're always, each iteration is accessing the next element in data. This is really good for optimizing on caches on the CPU, because you can go all the way down a cache line and reuse the whole cache line. It's nice on the CPU as well because you can use the SIMD instructions very easily. You can load contiguous data elements into a vector register and perform a vector operation. Well, I've come across code like this on the left multiple times. It's actually a fairly common pattern where we have a large array here, A, which is n by m in size, and we'll just assume that those are fairly large. And then the last dimension is here 2. And 2, actually, I encounter this quite often, 2 to 4 for these sorts of numbers here, something very small. Now, there's a couple reasons I've found out that people have done this. One reason, and this may sound silly, but one reason is just this extra dimension was kind of an afterthought, and so they slapped it on the end, not understanding what this means for the data access pattern. They simply add this on because they needed it, and that's a convenient place to put it. So I've seen that happen before, and I can understand how that can happen. A more common reason is that in these loops, if we're on the left, if you're running on the CPU, within that loop, I'm going to access element 1 and then access element 2. So my thread of execution, in this case, is still accessing adjacent memory addresses. So first I access element 1 of this array, then I access element 2 of this array, come back around element 1, element 2, and over again. And you can tell actually by looking at this that I converted this from a Fortran code, because I should be saying 0 and 1 here. So that sort of approach is very cache friendly, but is not very vector friendly. Now, the compiler can do some restructuring, and there are ways the compiler might still vectorize this. But in terms of just making things simple for the compiler, we're optimized along our cache line, but we're not optimizing very well for vector instructions. And so each iteration of the J loop, which is our fastest loop, strides through memory by 2. It accesses 2 elements and then moves back around. One restructuring that I've seen a lot of success with is taking that last dimension and moving it to the front, as you see on the right. So what this has done is now on the J dimension, the J loop is the fastest loop, and I'm accessing the A array always along this fastest dimension. So in C or C++, the fastest dimension is the farthest to the right, and on Fortran, it's the farthest to the left. So now, this data access pattern is still friendly through the cache, because successive iterations of J will access along the IJ cache line 1 here, and the next, and also the cache line of the element number 2 here. So we still get the cache optimization going down there, and it's fairly straightforward if the compiler vectorizes the J loop, that they're going to be able to access adjacent stride 1 memory addresses along each of these 2 arrays, or each of these 2 parts. So this restructuring, frequently we see a fairly large performance speed up on the GPU, is that it encourages an efficient use of the memory subsystem. And if you're more interested in that memory subsystem, I encourage you to go back and watch some of the GTC seminars where we talk about optimizing for memory and memory coalescing on the GPU. But this data access pattern works very well on GPU and tends to work very well on a CPU too. On the CPU, the time that you might see a performance degradation is if this loop is very, very long, and then you might see a poor cache reuse pattern. But for very short loops like this, which I frequently see, this works fairly well. Now, related to this, a similar sort of pattern that I see is instead of having a three-dimensional array on the left, is you might have a two-dimensional array of structures. So here I have a structure that contains two elements, A and B. A I'm loading with 1, B I'm loading with 0. And again, on the left, we're striding, in terms of the J loop, we're striding through memory by accessing every two elements. Now, within the loop, these are very likely to be adjacent memory addresses. But if you look across J, we're skipping through memory. The restructure that I've done in the past with that is to split it into two separate arrays, one for the A element, one for the B element. And a code that I encountered within the last several weeks, I did this restructuring, and for the function where it was being called, there was about a 20% performance improvement just from making this change. And the reason for that was this is a more appropriate way to access the data in memory. It sped up the GPU version by quite a bit, and the CPU version was slightly faster as well. And so now they're going through and encountering this, making this change to their data structures throughout the entire code. So it's very important that you think about the data structures and ensure that your innermost loops are always accessing your data elements in a stride one way. And this is, you can see very large performance benefits by making this change. Okay, so those are the general optimizations that I wanted to make sure that you're exposed to. Obviously, there are many more that you may encounter as you go, but if you can keep in mind the collapse clause, the tile clause, and accessing memory in a stride one manner, you're a good chunk of the way to getting, being able to optimize your code. Now, one other thing that I want to make sure you're exposed to before you go off and try to port your applications is the OpenACC routine directive. So many of the codes that come to the GPU hackathons that we hold and just the codes that I've encountered, it's a fairly common pattern to have some loops that are fairly coarse-grained. I mean, they're operating on they're operating in parallel, but in a coarser manner, and they call into functions, and those functions then have loops that operate in on the actual data, and these are where the fine-grained parallelism occurs. For many of those codes, they need to insert OpenACC kind of high in their program structure, high in their call tree, and call into multiple functions. A function, the main might call into a function that calls into another function that eventually calls into a function that calculates their derivatives, for instance. This structure is fairly common. Now, with OpenACC, you have two options to support this. If your compiler is able to inline all of your functions, then it's actually fairly easy to parallelize that sort of code. And in fact, with OpenACC 1.0, the requirement was that if there's a function call within a parallel region, it had to be inlined. But OpenACC 2.0 introduced another way to handle this so you can keep your code structure in place, and that's with the OpenACC routine directive. And this informs the compiler that when you encounter this routine, this function or this subroutine, that it needs to generate a device version of that. Something that when I'm running on whatever the device, a GPU for instance, that it can call into that function. Now, in order to do that, it actually needs two pieces of information. One, it needs to understand and know that it has to generate this function, but it also needs to understand what level of parallelism the function uses. So we talked last week about gangs, workers, and vectors, and so you can tell the compiler, or actually I shouldn't say you can, you must tell the compiler that this function or this subroutine will utilize a certain level of parallelism. And the reason for that is when it's building the code that calls into that function, so you have an ACC parallel loop somewhere that calls into this function, that parallel loop needs to know what parallelism is available for it to use. So gang, worker, vector, and then also SEQ, which is for sequential. And a sequential would be if every loop iteration calls into a certain function, you would make it sequential, meaning there's no parallelism there. And in my experience, the vast majority of codes I've encountered, use ACC routine sequential. And in fact, the lab that I'm going to encourage you to do at the end of this this lecture, it does require an ACC routine sequential in order to build the code. It's important you must specify one of these and exactly one of these on an ACC routine. The bind, the no host, and the device type clauses are really not that important, and I've put up here just for completeness. So let me show you how it's used, and since you'll need this during the lab. The routine directive appears at the declaration of your function. So in C and C++, that's typically in a header file. So here I've declared that I have a function foo, and that foo will be called from all iterations of a loop. And so that's what this pragma ACC routine is. So now the compiler knows when it encounters foo, it needs to build a version that will run on the device, and it will run sequentially. Then at the call site, so you see down here, I'm calling this for main, I have an ACC parallel loop, and it calls into foo. And because I've put this routine sequential directive at the function declaration, it knows, the compiler knows when parallelizing this loop that it can count on being able to call the foo function. So that's how you use it in C and C++. Fortran, similar but slightly different syntax. It does happen again in the function declaration, but it can be a little bit tricky. The way I tell people is it appears between the implicit none, because all good Fortran programmers please use implicit none. It appears between implicit none and the first variable that variable declaration, as I've shown here. In this slide, I actually use kind of an optional version. You say ACC routine, and you can pass it in the name of the function, but you don't have to. So ACC routine foo. So that's how you use it in Fortran. And I need to note for both the C, C++, and Fortran that if you have nested function calls, so if you have a function that calls into another function, at every single one of these declarations need to be decorated with ACC routine. So at each step, and that includes the parallelism. So that's how you use ACC routine. You'll have an opportunity to use this in the lab a little bit later. Okay, now I want to talk about asynchronous programming using OpenACC. So asynchronous programming, if you're not familiar with this term, it's programming in such a way that multiple operations can occur without immediate synchronization. Now I say immediate synchronization because anytime you do multiple operations, eventually you do need to synchronize and find out when that data is used. But if you program in such a way that independent operations can occur independently, without synchronization, then that gives the runtime and the hardware the opportunity to run them first in any order, but also potentially run them at the same time. So what are some real-world examples of being asynchronous? If you think about when you're cooking a meal, let's say I want to boil some potatoes, I'm going to make some mashed potatoes, and meanwhile, while they're boiling, I might go off and cook some other vegetables or cook the meat or whatever. So these are different operations that can occur asynchronously, and then at some later point, when it's time to build my plate, put the food on the plate, I'll synchronize all of the different parts. Similarly, let's say 3 students are working on researching the life of George Washington. One of these students might research his early life, find out, did he really cut down an apple tree? Another, his military career, and a third might focus on his presidency. Well, all 3 of these students can research these parts independently without synchronizing with each other, and then when it's time to write the final report, then they'll synchronize on what they've learned. So this is, again, 3 asynchronous operations, researching the early days, the military days, and the presidential days. Lastly, in the example that I'll use again for this coding example, is an automobile assembly line. So every single station along an assembly line adds a different part to the car. So I can have one station that puts wheels on, another station that puts bumpers on, another station that puts doors on. And we don't necessarily need to coordinate among all three of these. We just need to know that when this step is complete, it'll move on to the next one, and these steps can work asynchronously with each other. So how do we exploit this with OpenACC? So far, all of the directives we've used have been synchronous with the host CPU. So when I launch a parallel loop, I say ACC parallel loop, the host thread is going to wait until that parallel loop has completed. Similarly, if I have a data directive or a data region, the host thread is going to wait at the end of that data region so that when it's done, when the data region is complete, then the host thread can use that data. So everything has been done synchronously, and this is a really convenient way to write your code because you can kind of count on the data and the operations will have completed before they're needed. But most OpenACC directives can also be made asynchronous with the host. And so if you think about, if I have multiple parallel loops, I can say ACC parallel loop, return to the CPU, launch another ACC parallel loop either on the same device or a different device, launch another one, and then at a later time, synchronize and wait for the results. Similarly, if I put work onto a GPU, the CPU might decide to do other things. It might do a different part of the calculation, or maybe it writes some of my data out to a file while the next results are being calculated. Or probably the most common use is I could launch the data transfers for my arrays asynchronously so that they can be moved to the device before they're needed and allow for overlapping computation and data transfers. And this is what we'll be using the asynchronous programming to achieve. So the specific technique that we're going to use is known as pipelining. And the idea of pipelining, like an automobile assembly line, is to break up your calculation into smaller parts. And each of those parts then gets calculated in steps and performed independent of each other. Now, just because I program something asynchronously doesn't mean that things will happen at the same time, but I am making it so that it's possible to run these things at the same time. Just to give you a term here, a pipeline stage is a single step along the process. So it's generally, one part of the calculation is considered a pipeline stage. Now the code example I've written up for you is a fairly simple image filter. It doesn't do anything special. You're not going to probably see this one on Instagram or anything like that, but I've taken a filter that reads in an image like the one on the top. It applies a very light blur to the image and then inverts the color. So nothing exciting, but it does make some transformations. Now what's great about image sort of manipulations is that they're inherently parallel. Every pixel can be calculated independently of other pixels, so it really makes these sorts of operations simple to do. The skills we're going to use here, we're going to start off with a code that is parallelized on the GPU using OpenACC. We're going to use data regions and the update directive that we discussed last week. And then we're going to talk about making the work asynchronous using OpenACC's async clause and wait directive. And the process is we're going to build up a software pipeline. So here's the simple code. I've kind of extracted the core of it here, where I have a parallel loop that goes across every pixel of the image. So here I'm going across, the Y loop goes across all of the rows, and the X loop goes across all of the columns and visits each pixel. Inside that loop, I have the filter. The specifics of this filter aren't necessarily important, but it basically does an averaging of a pixel with some of the pixels around it to create a little bit of softening or blur effect. And then when I save the output, I invert the colors. That's what the 255 minus this calculation is. So this is just kind of the simple code. Now, I can build this and run it on the GPU. One thing I will point out before I show the GPU profile is because I want to parallelize across all of the pixels, I've specified that these for loops are gang and vector. So I'm just telling it just parallelize those, and implicitly I've told the compiler run these other loops sequentially. I could inform the compiler, use ACC loop sequential to tell the compiler explicitly to serialize these, but I'm counting on the fact that by making this outer loop gang and vector parallel, that's what the compiler will do. And so I did that to save some space here on the slides. Here is the timeline if I run that operation, and it's as you would expect. The big purple block in the middle is the actual calculation that's occurring to manipulate the image, and the brown boxes on either side are the data transfers. So something to notice is that roughly a third of the runtime is occupied by data transfers. By clicking on the various boxes, I determined that we're running for about 3.2 milliseconds we see up at the top for the entire calculation, and about a half a millisecond, 500 microseconds for each of these data transfers, and that works out to about a third of the transfer. Now, what if we could overlap those copies with the computation? Here I've shifted the green boxes in. If we could do that, well, a little bit of rough math, kind of a back of the envelope calculation here. I'm taking 3.2 milliseconds. I'm taking half a millisecond to copy the data to the device, another half to copy the data back. And so I would shave off 1 millisecond. And the net result is a little shy of a 1.5x performance improvement is possible if I could get rid of these data transfers. So how might I do that? I need to find a way to move my data transfers so they overlap with my computation. But obviously my computation can't complete until I've done the work. So we're going to want to block, but to break up our work in order to enable overlapping. So pipelining is the technique we'll use, and I've got here two cartoons. The first one shows, okay, I've got two operations, and each operation requires copying data from the host to the device, operating within a GPU kernel, and copying the data back. And then the next operation does the same thing. Data to the device, runs, copies data back. And as I work, you can see that I've sequentialized all of these steps. Down the bottom, though, if I exploit the fact that these are independent operations, well, then I could start my host-to-device transfer, and then as soon as it completes, start queuing up work for the next kernel while the first kernel is running. And then when it completes, the first kernel completes, I start copying data back. The second kernel is ready to begin executing, and it'll execute, and I can start queuing in data for the next one. So you can see I build out this pipeline. And the thing you'll find here is that you can actually get a lot more work done in the same amount of time by stacking up these operations and exploiting the fact that these are independent of each other. So in fact, if I were to add a fourth row here, you'd see that I could actually complete 4 independent operations in the same amount of time that it takes to do 2 serially. Now, it's worth noting, cartoons like this make things look really nice. Everything, all the boxes line up beautifully. Real applications, they never quite line up like this. Balancing the exact size of the work with the exact time it takes to copy the data is essentially impossible. It's very difficult to do, but it does make for a nice cartoon. So in order to achieve this in our code, is we need to break up our work into parts, into smaller parts that we can overlap. So you can see on the left, I've actually taken the picture here, and I've broken it into 2 parts. I've already filtered the top part, and I'm waiting to filter the second part. Because on this image, every pixel is calculated independently, we can really work on parts of the image rather than having to work on the whole thing. So I could break this up by rows. I could break it up by columns. I could break it up by 2D tiles. And work on them in that way. And I've actually decided for convenience to break this up along rows. So I'll have in the actual code 8 horizontal bands that are operated on independently. You can really take this to the extreme. You can operate on each row independently. You can even operate on each pixel of each row independently. But you have to strike the right balance to find the best breakout. So in order to do that, we do need to change the code a little bit. And here I've shown you an example of how we've done this. So before we had the X and the X and Y loops And we've added an additional loop along the outside that blocks up the Y, and Y is, again, the rows of our image. So I come in, it does n blocks iterations, and for my example, I've done 8 blocks. It calculates what's the starting row and the ending row for this, and then the next step is I modify my Y loop, so I'm only operating on the rows within each single chunk. So a very slight modification here. So instead of going from 0 to the total height, I'm going from the starting point inside my chunk to the ending point. Next, I added data region. And the reason I had to add this data region is we no longer want the parallel loop to be copying the device, the arrays to and from the device, or the image. And copy the output image out.
Hey, Jeff, you
Yes?
broke up for a second. Can you repeat the last sentence? Thank you.
Sure. So we've step 3 of this process is adding a data region to this computation. The data region ensures that we're copying the data, the input data, in this case it's called image data, to the device before the blocking loop, and copying the final results out rather than copying it at each parallel loop. And if you note, there is also a filter array that I'm copying here. So fairly simple transformation. I've just added one loop, and here's the new GPU timeline. We're doing this in steps, and notice here that at the end of this step, I've broken my computation up into 8 parts, and that's these 8 purple boxes. I still have all of my data transfers at the beginning and the end, but I am operating on smaller parts. And my runtime actually went up a little bit, and that's okay, because we're only doing this one step at a time, and I've added a little extra overhead by blocking it up. So what we would really like to do is have each of these purple blocks copy in only the amount of data that it needs, and copy out only the amount of data that it affected, so that we're really operating on independent blocks of the image. Now, we talked about the update directive last week, and I'll show it to you again. The update directive specifies an array, or in the case that we're doing here, a part of an array that needs to get refreshed within that data region. And what I mean by refreshed is the host copy and the device copy are made coherent. They're made the same. They're made to agree with each other. So I can use ACC update host or update self to update the host copy of the array, and I can use ACC update device to update the device copy of the array. So we need to break up our data motion, and to do that, here's the code. So first, I changed all of my data clauses from copy in and copy out of the array or the image to only creating space. And so now there's no data movement that's going to happen at this up here. Instead, I'm just going to create empty arrays for the input value and the output value. Next, I add an update device directive, and that tells the compiler I have to figure out what is the starting point and the ending point of my slice of the image, and I update just that slice. And if you're paying close attention, I'm actually updating that slice plus a couple rows because of the way the filter works. And so we have kind of a ghost zone, if you're familiar with that term. And lastly, I'm going to copy the results back one block at a time. So now within this operation, each block is responsible for copying its part of the data to the device, operating on just that part of the data, and then copying that part back. So now we've made these independent operations of work. And here's our new GPU timeline. So now, if we look closely, for every purple box here, which is our image transformation, I copy data in, I do the filter on the image, and I copy the data out. And then I do the same for the next block and the next block all the way down the line. So now we've built up a case, and I should point out that as you're implementing something like this, at every step of the way you have to stop, check your results, and make sure that you're still getting the expected results. And that's why we're doing it in a step-by-step basis. So the last thing here is to make it asynchronous. And OpenACC uses a clause to make things asynchronous, and that is the async clause. So OpenACC defines something called asynchronous work queues. And so everything that goes into a queue operates in the same order. It's first in, first out. So if I put in a data transfer and then a computation and then another data transfer, it will happen in that order. That is the work queue. But it does allow you to have multiple work queues. And so the async clause will say, take this operation, launch it to a particular work queue, and if you don't give it a number, it chooses the default queue, and then immediately return as soon as possible back to the CPU to do more things. And in our case, the more things we want to do is put more work and more work and more work. Now, eventually, we put a bunch of work over onto the device, put it onto the GPU, and eventually we do need the results back, because otherwise what's the point of doing it? And so there's also a wait directive which is used to synchronize with the work queues. So you can see down the bottom I have two parallel loops that I put into the asynchronous queue number 1, and then at the bottom I do an ACC wait on queue 1. And if I don't put a number into ACC wait, it'll wait across all queues. So this is how you make things asynchronous. We launch the work to the device, we launch the next work to the device, and then eventually the host CPU will wait for that work to complete. So let's add that to our code, and we're almost done with this code. So the major change I made here is now my updates, both updates and my parallel loop go into asynchronous work queues. And I figure out that the number of my asynchronous work queue, a convenient way to do that is to use my block ID. And because work queues are a little bit expensive to create the first time, I actually like to reuse work queues. So here I've chosen, I'm going to take the block ID, I'm going to do modulo 3, so I reuse 3 work queues. One queue will be copying data to the device, another queue will be executing, and the third queue will be copying data from the device. And note, I did a +1 here because on NVIDIA devices, work queue 0 is kind of special, so we try to avoid that. Of course, if I'm going to put work into these work queues, I need to wait at the bottom, and it's very easy to forget this wait. And as you're doing the lab that we're assigning a little bit later, it's very easy to forget to add this wait for all the work to be done. So looking at the slide, what happens is I come into my block loop, I copy the data from my first block to the device, I launch the execution of my first block to the device, I enqueue the copy back of that block to the device, and I come back around to the same thing for the next block, and the next block, and the next block. And eventually, once all of the blocks have been sent to the GPU, then I wait for the results. And here's what the GPU timeline now looks like. And you can see that I now have these blue blocks down the bottom. These are my kernels, and you see I have to pay a little bit of cost at the beginning to copy my first block of data to the device, and a little bit at the end to copy the last block, but all of the other data transfers are completely overlapping computation, so they've become essentially free. So by breaking up my computation and applying this pipelining, I've achieved a speed up. And to give you an idea here, my original code, which was running in parallel but doing the copy first but at the beginning and the end, is my baseline. I blocked it up. It slowed down a little bit. That adds a little bit of overhead in breaking up the blocks. I inserted the updates so that all of the updates happen per block, and that actually slowed it down a little bit more too because I added some additional overhead. But then when I made them asynchronous so that I can pipeline and overlap, you can see I got just shy of 1.5x. And actually, this is the same number that we estimated we would get by earlier in the process by eliminating our data transfers. So, so the net result was quite a nice speed up. Now, the reason I present to you these middle steps is just for correctness. It really is a case that If I did all of this at once in one step, it can be very error prone, and I'll end up with, if I get incorrect results, I don't necessarily know where I introduced the error. So by doing it this way, first blocking, checking to make sure I get correct results, then breaking up the data transfers, still make sure I get the correct results, and then to keep it asynchronous, you can see I got a good performance improvement, and I ensured that I had correct code. So this is asynchronous or software pipelining. Now, I do want to point out, because I get asked a lot, and I think in both of the previous lectures, someone asked, well, what about using multiple GPUs with OpenACC? Can you use multiple GPUs? And what I like about pipelining examples is once you have broken your work up into these independent chunks, it's actually fairly straightforward to take that code and then start sending the chunks to multiple devices. Because all of the work is independent, it doesn't really matter that whether they're done on the same device or not. And so I didn't get a chance to take this, this image filter code and begin running it across multiple devices. But the code that you'll be doing in the lab after this course, I do have a multi-GPU version of that. So here, this is a code that you'll see in the lab that generates a Mandelbrot image. It's a fractal generator. And I've applied the same technique where I have, let me get my pointers here. I have a blocking loop here. I have the work that does the loop, and here's my data region around all of that. So this is the exact same format we just had. Now the difference is what I'm doing is I'm calling the ACC set device num function to tell the compiler, or more specifically tell the runtime, which GPU I want to send my OpenACC directives to. And so this is can be called from C or Fortran, and I say, in this case, I've chosen to send, I could say send to device 0, the work will go to device 0. If I say 1, it'll go to device 1, and all directives will go there until the next time I call AC set device. So what I've actually done, let me find my, adjust my pen here, is I've decided to use OpenMP around this. So here's an OpenMP parallel loop. Here's the parallel, and down below is the loop. And so what that's doing for me is I've set one OpenMP thread per device, and then I've assigned each thread using the OpenACC ACC set device num function to that device. And then all of the rest of the code is the same. It remains intact. And so what happens is my block loop down here, all of the blocks get broken up among CPU threads, and since each CPU thread has its own device, I just send that thread's work to a different device. So it's really pretty straightforward to extend this same idea to multiple devices. This code, as I said, is related to the lab that you have that I'm going to encourage you to take, and is available online, and we'll be sure to post a link so you can see this. And here is the dprof profile demonstrating what's happening. I have 2 devices, one that I'm showing here and one that I'm showing here, and you can see that they're operating. The work is being done. The blocks of work are being spread across those 2 devices. So once you have this technique of using this pipeline technique of breaking up your work into independent chunks, then it's fairly straightforward to use multiple devices using OpenACC. The last bit here, and then we'll be done and ready for questions, is interoperability. I can't stress enough that when you start using OpenACC, you're not saying, I buy into OpenACC and nothing else. OpenACC is a great mechanism for getting your code accelerated very quickly, but it does fit into the broader ecosystem, and particularly on NVIDIA GPUs, I want to talk about accelerated libraries and CUDA. If you go to the NVIDIA Developer Zone, you'll learn about lots of existing accelerated applications and existing accelerated libraries. And we want to make sure that you're able to use all of them. And the key directive that you need to see in order to use this interoperability is the host data directive. We talked about data directives. Data directives take the data on the host and expose that to your accelerator device. The host data can be thought of as the reverse of that. I have data that I've already put out on the host. So in this case, I've put the data out using my ACC data region here, and then I want to use my host copy of that data somewhere on, or excuse me, I use my device copy of the data somewhere on the host. And so I've inserted this ACC host data use device, and I've said for the X and the Y, use the device pointers. So it may not be obvious how this is useful until I show a few codes. So the first code here is I have on the right a simple CUDA kernel. It solves the single precision, the SAXB operation. So here's my function that calls the SAXB kernel. If you're not familiar with the syntax, I'm launching 4,000 thread blocks of 256 threads. And this is the routine that I call. Now, I'm expecting X and Y to exist on the device. And so in order to call that, I'm going to use the host data use device directive on the left. Here I'm showing Fortran, and the reason I'm showing Fortran is just to demonstrate that you can interoperate between the languages however you'd like. It works in C, C++, and Fortran. And what happens here is I've initialized X and Y on the device up higher. When I encounter this code, I tell the compiler, for this limited region of the code, any functions you call on the CPU, pass in X and pass in Y from the device. So SAXB receives the device copies and launches the CUDA kernel. Of course, SAXB is a fairly simple code. In fact, you probably would want to just call it from kublas. And so here's an example where you could call from kublas. I'm calling the kublas SAXB. This is colored blue because that's actually called from the CPU. But because I've used this host data directive, it's getting device data. So this works with kublas, this works with cuFFT, this works with Magma, with Thrust, with any of the accelerated math libraries. And people have asked me if it'll work with some of the deep learning frameworks, and as far as I know, it will, but I've never tried it myself. We have lots more examples of this particular approach. If you want to go back to the advanced OpenACC course we gave in the spring, one of my colleagues actually demonstrated how to use this with MPI to exchange data between two different processes directly from GPU to GPU. And also, we have a blog post online. If you search for, I think it's called 3 OpenACC interoperability tricks or something like that, you'll find a blog post that I did, and I put a bunch of examples on GitHub of how to do this. So I'll have Julia send out the link to that as well. Okay, so to end out, I want to remind you about our Quick Labs system. Quick Labs, as part of this course, you can take we'll provide you credits to use our Quick Lab system. You don't need a GPU. The GPU is provided. Everything is done inside your web browser, so it's really simple to get started. If you haven't already, go to this link here. You sign up with the promo code OpenACC16, and you'll get enough credits to do all of our OpenACC courses. Here you'll see a screenshot of Quick Labs, and there's a bunch of courses here. The one that I want you to look at for this week is pipelining work on the GPU with OpenACC. It takes the same technique that we've done here on a slightly different code and teaches you how to do it hands-on. So I encourage you to go back and do that. And if you have questions, email us, openacc@nvidia.com. As a reminder, if you do you complete the Quick Labs and want to get started on putting OpenACC into your own code, I encourage you to check out the OpenACC Toolkit, which is available off of developer.nvidia.com. This is free to anyone affiliated with the university. If you're not affiliated with the university, you can get a free 90-day license. Also, if you want to pick up a book and learn more about OpenACC, it's now available here. There's a book called Parallel Programming with OpenACC. And that's the picture on the left here. And lastly, as Julia said, beginning tomorrow, we will have a form available for you to fill out, take a quiz that demonstrates that you've completed this course, and by completing that quiz, you will be entered to win either a copy of the book or even possibly a Titan X GPU. So I'll leave up the where to find more help, and at this point, move over to the questions. The first question was, is there any word about Microsoft supporting OpenACC in Visual Studio? And I'm not aware of any effort in that vein. The PGI compiler is available for Windows. I know there's the Visual Fortran compiler, and that's one route that you can use. But as far as I know, the Visual Studio itself, there's no plans to integrate OpenACC. The name suggests free for all software as an OpenCL, OpenGL. Why have we chosen this name for commercial software? This is OpenACC is a free standard. It is an industry standard that is written by a variety of members. Some of the members are other industry partners, other national labs. For instance, OpenACC was founded by PGI, NVIDIA, Cray, and a company called CAPS, PatScale, AMD, Oak Ridge National Labs are all now members as well. So this is an open and free standard. It's actually backed by a standards group in a similar vein as OpenCL and OpenGL. So that's why this is this. OpenACC is the standard. The PGI compiler itself is a commercial compiler, but it is only one of several implementations. GCC has a freely available OpenACC compiler. You can also get OpenACC compilers from PatScale and from Cray. Can I please provide links to the sessions on optimized GPU memory? Yes, we'll definitely do that. The one I specifically would recommend checking out is called, I believe it's called Memory Bandwidth Bootcamp or Memory Bootcamp. I encourage you to check that out. That was at GCC 16. If you go to gputechconf.com, the link here, and search for Memory Bootcamp, it should pull that up. So there's a question. Let me go back to slide 10 and which was, I think, so right around here. There's a question about the use of the dot syntax here. Specifically, it's talking about, well, if you had a class A, it may be more efficient to say class A dot A and have a array of those of the A elements. That's absolutely, you're correct. Whoever put this in here, that another option is to have a structure, or in this case a class of arrays A and B. That's absolutely another option. So you might say instead of having separate arrays, you might, if I can draw in here at the green, do class A or structure A dot A with the array. So you're absolutely correct. The point of this is to demonstrate, though, that you do want to have stride 1 memory accesses in the fastest dimensions. That's the reason for that. And so yes, you're correct. This could be changed into a class or a structure that contains the A and B arrays. Is there a possibility of running a sort loop within a C# program? C# is not a supported language with OpenACC. OpenACC supports C, C++, and Fortran. You could certainly parallelize a C++ loop using OpenACC, or if you're interested in the high-level interface, I would point you to Thrust. And one of the examples I have for interoperability is using Thrust, using OpenACC to manage the data and actually calling the Thrust array sort operation, which can be done on the GPU in parallel. So, so not for C#, but for C++, certainly possible. So there was a question here about whether async would work with unified memory, so even for kernel concurrency. It is possible to use async with unified memory. It will kind of depend a little bit on the implementation about whether about exactly how the data transfers would occur. So on a Pascal P100, for instance, the compiler might choose to use async as a hint to begin asynchronously prefetching your data. But you're correct in a sense that if the data is already on the device because it's unified memory, that the async data transfers themselves would not work. However, the asynchronous kernels would then still be able to operate in the same way. So the pipelining might look a little bit different. There was some question about whether the async clause would assign to the default queue. If you say async and don't pass in a queue number, or if you pass in 0, that will go into the default queue. So that's why we do things a little bit differently. So the async clause with no option does go into the default queue. So there was, again, a question here about when using async and wait with the queue numbers, does the default queue have a number? I need to double check the spec. I wonder if I can bring the spec up another window here to double check. I think there's actually a specific queue number that's something like ACC default queue. If you'll give me just 1 second, I'll actually look up the answer to this. So when we call the async, 216, here we go, asynchronous behavior. I think if you say, you can call it with either ACC async and not put a value in there, or the special ACC, the special integer ACC async no val that is defined in the spec as the default queue. Another interesting thing that that I probably should make you aware of is there's also a special queue that's the sync queue, and so if you're debugging, you could actually change all of your asynchronous values to point to ACC async sync, and that will make everything synchronous just for the point of debugging. So the question of how does one pick the optimal numbers of work queues for asynchronous work? Really, the truth is experimentation. The thing to keep in mind is at most, you can have one data transfer coming from the CPU to the GPU, one data transfer coming from the GPU to the CPU. So there's 2 queues for data transfer, and then you might have, you probably want one more for work. And so really, 3 to 4 is probably about the best that you're going to get, and I use 3 here. You can experiment, and sometimes you might find more will help, but that's usually only the case if you have very, very tiny compute kernels that don't do much work. Assuming that your compute regions actually do a fair amount of work, then 3 to 4 is probably really the maximum that you're going to want, because you'll get both directions of data transfer plus the computation going on. Now, there was a good question here. Someone asked on my multi-example here, if I can come down to my multi-GPU, someone asked me why I used OpenMP instead of using a multi-core CPU versus OpenACC, and that actually has come up in some of the OpenACC standards meetings as well. OpenACC does support nesting, so you could have an ACC parallel region on the outside and another ACC parallel region on the inside. The PGI compiler, at least, does not currently support mixing 2 different targets like that, and hopefully at some point in the future we will be able to do this with just one. Really, using OpenMP here was as much a demonstration that the 2 specifications can be used together as anything else. But there's no reason OpenACC couldn't be done with nested OpenACC, but the compiler that I was using doesn't support nested OpenACC in that way. There was a question again on this particular slide, is why did I need the async calls, the multiple async queues on this example, since each device is already going to be operating asynchronously from each other? And the reason for that is I'm going to have each device working asynchronously, but I'm still going to be copying data to each device and from each device. So by using further queues, I can actually have a pipeline going on each device and speed them up some more. So if you look on the queue here, if I didn't use asynchronous, I wouldn't get the additional overlapping that you see on each device. So it just kind of allows me to further optimize things. I certainly could operate on each device synchronously, and I'll still get 2 different devices. By operating asynchronously, I can also overlap the data transfer to and from each device. So that's why I did that. Okay. So there's a question here of in CUDA, you may run out of GPU memory, and then you need to, if you're using very big arrays. Does OpenACC do anything to manage these limitations? Not directly, unfortunately. There's if you run out of GPU memory by having large OpenACC arrays, the compiler, or actually the program is going to crash at runtime. So it's kind of unfortunate. There are mechanisms within OpenACC to mitigate this. One in particular is it does provide a mechanism, and let me remind myself exactly what it's called, but a mechanism for allocating a space of data and implementing kind of a sliding window where we reuse that data multiple times for different parts of the array. If I can find it here real quick, it's ACC map data and ACC unmapped data. And so what that would do is I could say allocate as large a buffer as I can. I map that to a part of my data. I update the data to the device, and when I'm done, I unmap it and reuse that. Run out of memory.
Hi, Jeff. Can you repeat the answer to the last question? We lost you for a bit.
Nope. Yes. So the last question was about if your GPU runs out of memory, what happens? And what happens with OpenACC is that, similar to CUDA, is the program will crash. I would point to two functions, ACC map data and ACC unmapped data, as mechanisms to mitigate this and allow you to reuse a single large allocation throughout your run. And but otherwise, yes, you will crash if you run out. And if you give me just a second, I'll switch my audio so that hopefully this won't continue to happen.
So while Jeff is working on fixing the audio, I wanted to remind everyone that the certification will be open starting tomorrow, November 10th. We'll keep it open till January 1st, so you all will have time to finish your quick labs and take the certification test or get any questions you need answered before you take the test. After January 1st, we'll do the raffle, and the winners will receive book or the Titan X. So we'll get that done. Meanwhile, if you have any questions, please send them to openacc@nvidia.com if we did not answer them today. And also, all the recordings have been posted to OpenACC course page. I will post the link one more time so you have it for your reference. And I have also posted the link to the workshop that, the boot camp that Jeff mentioned, the memory bandwidth boot camp. It's been done at GTC last year, so there is a link for you to access it right now as well.
Thanks, Julia. I'm back, and hopefully this audio will work a little bit better. The next question I see is how well will OpenACC be supported in the future? Is there enough funding, et cetera? And right now we're seeing a lot of growth in the adoption of OpenACC, and we believe in it. We're certainly committed to continuing to develop it and support it, and right now it seems like the momentum is really building. So we believe it's going to be continue to be well supported. It's going into it's in GCC, the compiler, and is being further developed there. And there's multiple other compilers available, both commercial and research compilers. So yeah, we believe it's going to continue to be well supported and only support more targets. So I'll point you to there's several articles that have been released over the past week talking about future versions of OpenACC, and it talks about the additional targets that have been released, including ARM, power processors, GPUs from both NVIDIA and AMD, and future support for additional ARM targets, as well as x86 mini cores such as the Xeon Phi. So it's definitely, we believe it will continue to be well supported in the future. Another question that came up was around my example where I'm calling CUDA from Fortran. Can I describe a little bit more about the C kernels and using OpenACC? So the code on the right is using CUDA C. It is so that's the top part here where we have this global keyword. This is what we would call the compute kernel. It gets called in parallel and operates on all of the data elements. The code on the bottom is a function that I call from the CPU, and it launches that kernel in parallel. So the launch parameters are, I want thread blocks with 256 threads, and I want 4,000 of them. So that's what's happening on the right. So I have a compute kernel, and I'm launching that using CUDA C. On the left, it is a Fortran program, although it easily could be a C or C++ program as well. On the left, I'm using OpenACC to manage my data. So, I think in the full example as it appears on GitHub, and I'll paste that into the chat in just a moment. The full example initializes the array and then calls into this Saxby routine on the right, and so that's what's happening down at the bottom here. I'm calling into Saxby. Saxby is the code on the right, and I'm passing in the device copies of X and Y, and so that's what's happening here. I'm going to paste over here to all attendees a link to a GitHub repository where I have lots and lots of examples using Fortran, using C, using CUDA C, using CUDA Fortran, using Thrust, using device-side CUDA. There's just every kind of example I could come up with on how to interoperate between OpenACC and other things. So I'll kind of point you to that. The second part of the question is there a way to write Fortran GPU code without using CUDA Fortran? No. You can, the Fortran GPU code, you would either want to use CUDA Fortran, which is supported by PGI and the IBM XLF compiler, or use OpenACC in your Fortran to have the compiler generate the code for you. Is OpenACC reserved to the NVIDIA GPU? Described optimizations can be utilized only on the NVIDIA GPU. No, OpenACC, as I said earlier, is an open standard, so it is available on a variety of devices, NVIDIA GPUs, AMD GPUs, multi-core x86 CPUs, multi-core power CPUs, multi-core ARM CPUs. All of these are available. Some of the optimizations may differ a little bit, and one of the things I talked about in the previous lecture is that we do provide a mechanism to say, all right, if I'm tuning, say, the vector length of my loop to a particular architecture, only apply that optimization here, and any other architecture I encounter, let the compiler choose for me. And so that's the device type clause. So if you'll refer back to last week's lecture, we talk a little bit about that. Now, some of the, when you're operating asynchronously, that's something that may not apply to all targets. So what does it mean to launch this code asynchronously if I'm building for a multi-core CPU? Probably doesn't mean very much. It basically will be forced to run it synchronously across the multi-core threads. But nonetheless, I've exposed that into the code, enabled it when on targets that support asynchronous and concurrent execution to take advantage of that, and on targets that don't support this, don't support operating on these chunks in parallel, then they won't. So that's kind of where that comes in. How can transfers be done between GPUs? Currently, there's not a clean way to do it between multiple GPUs. You can use MPI if you want to run multiple processes and use MPI to pass data between them. This was demonstrated in the Advanced OpenACC course. But we've talked about adding a sorry, I'm double checking whether we already have this in the spec. We have talked about adding a yes, we do have an API routine that will copy from
between two GPU pointers, but I think actually that only works on the same device. So currently, unfortunately, the best way to handle copying data between two GPUs is either to use MPI to do it or to copy back to the host and copy back up. That's something that we're aware is a limitation that we're trying to work through. Let's see. That's kind of related. There was a follow-up question from the same person about staging the pipeline across multiple GPUs, and unfortunately, without the direct data transfers, we don't currently have that. One person asked, I mentioned OpenMP, and they said, okay, I've heard of CUDA and I've heard of OpenACC. What is OpenMP? OpenMP is another programming language for directives that was specifically designed for running on shared memory platforms. It generates threads. It runs. You can take your loop iterations and spread them across those CPU threads. And so that's what I'm doing here. I am using this OpenMP parallel. This generates some number of OpenMP threads. In the actual example code I have, it queries how many devices I have and launches that many CPU threads. And then within that, I have an OMP4 here, and that takes the iterations of this loop and breaks them across those threads. You can use this in place of, say, P threads or C++ threads as, again, a simple high-level mechanism for taking your work and spreading it across CPU threads. What is the best way to determine the amount of video card memory available due to, and can I reserve video memory for use with OpenACC? Right now, OpenACC does not have a direct means of querying how much memory is available. This is actually something we're planning on adding in the next iteration as a means to query that. The best way you could do it currently is to look into the CUDA APIs, and there's I believe it's called CUDA get mem info that will query and tell you the amount of data, the amount of memory that's free to be used. And so I would point you to the CUDA documentation about querying the memory and dividing the memory between video and computation. What is the difference between OpenCL and OpenACC? OpenCL is a low-level language where you write your own parallel execution kernels, and OpenCL provides library routines to manage the data between two devices. You have to explicitly manage the data, explicitly launch your work in parallel. So everything is done explicitly by you. It does aim to be portable across multiple devices. My experience is that it actually is not as portable as people hope, because the boilerplate code that manages your data and how you launch your kernel is fairly portable, but then the kernels themselves you need to rewrite. OpenACC, on the other hand, tries to represent things at a high enough level that you don't need to worry about that. So you don't have to worry about allocating 2 copies of your data and keeping track of those. That's handled for you behind the scenes by the runtime. You don't need to worry about generating an OpenCL kernel. This is generated for you by the compiler. There are compilers out there that actually implement OpenACC by taking the loops, parallelizing the loops into OpenCL kernels and launching them using OpenCL. So it's actually, the OpenACC is at the high level, and then the compiler generates the lower level OpenCL CUDA for you. That's that. GCC has patches to add GPU support for functions to OpenMP 4.0. Yes, that's currently in development. There's currently support for OpenACC 2.0 on NVIDIA GPUs in GCC, and OpenMP 4.0, which includes similar directives for offloading to Intel platforms. And there is work in the next version, GCC 7, of adding further support to both of those, and including GPU support for OpenMP. Which compilers can utilize OpenACC? there's the PGI compiler, the Cray compiler, the PathSkill compiler, GCC, and then multiple research compilers. There's one called OpenARC, one called OpenUH. There's one called ROSE. There's a compiler for the current fastest computer in the world, which lives in China, that's specially built for their machine. And there's at least one that I know of in Japan. So there's really a variety of compilers available for you. The most common compilers I encounter are PGI and Cray, and a lot of people are really interested in the GCC as well. But there's a variety of others available. So there was a question of, do I have examples that reference some of the deep learning algorithms like forward pass, back propagation, implemented using OpenACC because he wants to understand the other dependent libraries required to accomplish it. I'm not aware of anyone who has done this. Many of the deep learning algorithms really could be done using OpenACC. You can write, write the loops and parallelize them that way. But most of the deep learning currently being done is through higher level frameworks such as Torch, Theano, Caffe, TensorFlow, CNMK. These are all frameworks that have been written to do these, and most of the kernels within those have been written, are actually called out of libraries or have been written in CUDA. So I'm not aware of any efforts that have done these with OpenACC. One certainly could. I just don't know of anyone who has. Let's see if I can understand this. The last question I see here. It is not necessary to use CUDA. You can simply use OpenACC to manage data transfer, optimize parallel pipeline, all stuff. That's if I'm understanding the question correctly, that's correct. You can do, and the approach that I typically try to tell people is if you have a code and that you have absolutely no parallelism in, is to start off looking at accelerated libraries and see if there's any of the math operations you do that already have libraries available. Linear algebra, FFTs, things like that are common. Then use OpenACC to accelerate as much of your code as possible because you can very quickly take your existing code, put OpenACC in it, and quickly get it up and running. And then when all is said and done, once you've got the bulk of your code running with OpenACC, if you have reason to really hand optimize a particular part, you can do that with CUDA and still leave all of the data management and all of the other infrastructure in place using OpenACC. So that's kind of the mechanism I take place here. So we have about 2 more minutes if there's anyone that'd like to post some last-second questions. Otherwise, the remainder of the questions, I would say, I would point you to OpenACC at NVIDIA.com. Someone commented here, the profiling and parallelizing with OpenACC is not free. How can you do it? If you'll go to the link here and sign up, you will receive enough credits to do all of the labs. So sign up with OpenACC 16. This will apply enough credits to your account that all of the labs will be are available to you at no cost to you. If you've already signed up for Quick Labs and this doesn't work for you because you've already signed up for Quick Labs, email us, openacc@nvidia.com, and with your account details, and we'll make sure that you get enough additional credits to your account to make sure that you can do all of the labs, all of the OpenACC labs for free.
Yeah, well, also want to add regarding the Quick Labs, I see a lot of questions today regarding access. So if for some reason you don't have enough credits or they're expired or something else happened, you don't have access to the labs, please email to openacc@nvidia.com. We'll sort it out. Today there were also some overhaul by Quick Labs themselves. They did some update and a couple pages kind of in progress of going up to speed again. So please, again, email to openacc@nvidia.com. We will help you out to get access to the Quick Labs. There were also a question regarding if there are any more Quick Labs to do on top of what was already available. So we are working on adding more exercises, and Jeff can probably cover that in terms of the timeline and what will be covered. But there are also more ways how you can learn OpenACC. OpenACC.org is announcing a series of workshops that will be hosted around the world, and there will be targeted service optimizing your code, or if you don't have a code, you can come and join other teams to do so, and you will learn how to compile and profile this code, kind of be prepared to the next big step. OpenACC.org as well, together with the Oak Ridge National Lab, organizes a series of hackathons. Also around the world, they're usually about 5 or 6 a year, and this is very intensive events, 5 days a week, with 2 mentors per team, and it will be like kind of full deep dive on OpenACC. So all this information is available on OpenACC.org for all available events and workshops. So please keep an eye if you are looking for more ways to learn about OpenACC. This is a great resource. Okay, let me check if there are more questions coming.
I did answer 2 more while you were talking. One is someone asked about the OpenACC, the repository I referred to that has the OpenACC interoperability. I did respond to that with that link. And the last one I think is a great question to end on is what are the best debuggers for using OpenACC? And I'll point to Alinea DDT and TotalView. Both have support for OpenACC. There really are any compiler that understands CUDA will work with OpenACC, since once we get down to the the GPU, it looks the same to the debugger. But both the DDT and TotalView have added support so that they understand when a code is OpenACC and try to help you through that. So I would point you to those as well.
So there is also, I believe, one question for you, Jeff. Is it possible to do tiling from portions of host memory into GPU memory with OpenACC?
Oh, I missed that one. Is it possible to do a tiling, an automatic tiling, I'm assuming the question is, from host memory to GPU memory? And currently, no. That there actually has been some discussions around, what would that look like? Could we provide that capability? So it's not out of the question that we might do an automatic tiling like that in the future, but really, currently, the way you would do that is as I demonstrated here, where we manually broke it up to achieve the tiling, both to overlap to one device and to overlap across many. So unfortunately, we can't do it automatically, but here's the tools to do it manually if you like.
Okay, great, thanks. I believe with that we are about to close, and again, all the recordings will be posted on the course page. We have already posted the Q&As and lectures for the first 2 sessions, so you're welcome to check it out on the OpenACC course page and go through those again if needed. The certification will be available starting tomorrow, and we will keep it open until January 1st. We know that there are a lot of holidays coming in, and you're all busy, so we open up this window a little bit longer, so you have an opportunity to finish the test. We will announce the winners after January 1st, I believe the first week of January. There will be 3 winners because we have 1 GPU Titan X to give away and 2 OpenACC books. For OpenACC books, they are available already right now, and we're talking to the publisher to give people who attended the course a discount if you're willing to purchase. So probably by the end of the week, I will be able to give you a promo code if you're willing to purchase the book with some discount. I believe with that, I think that's it. Thanks a lot for participating in the course. We really appreciate your attendance and really high interest. Looking forward to hear about your results and your projects, and good luck with the certification. See you soon. Thank you.